Okay, hello everyone in a new video. So we have reached part 2 of chapter 7, which is the chapter of Newton's second law for grade 11 students. So we have reached section number 9. So let me say that the title of this section, applying Newton's second law. Or let me say application, okay, applying Newton's second law. So let me say that Newton's second law is given by sum of forces equal to ma. And we have specified previously that A represents the acceleration of the body, submitted to the forces that are given by the sum of forces. So we have several cases here. Let's start by discussing the case in which A is equal to 0. So this may happen to two reasons. So if the body is at equilibrium, so in this case we have that the sum of forces is equal to m multiplied by 0, which is equal to 0 vector. So sum of forces is equal to 0 vector. So this is given by the equilibrium condition. And in this case, the body is not moving. Now the other case, if the body is moving but at a constant speed or at a constant velocity. So if the body is moving but at a constant velocity, which means that if v is equal to a constant, so in this case the acceleration factor is what? 0. So notice that sum of forces is equal to 0 may be due to two reasons. Either the body is at equilibrium or the body is moving at a constant velocity. So in this case it is not at equilibrium, but we have also that sum of forces is equal to mass multiplied by the 0 vector, which is equal to the 0 vector. So in brief, sum of forces is equal to 0, which is using Newton's second law, may be due to two reasons. The first one is given by v is equal to a constant or at equilibrium. Okay, so now we are interested in solving the equation sum of forces is equal to 0. Now in this case we will follow several steps in order to solve this equation. Notice that this is a vectorial equation which requires projection. So step number 1, list the forces acting on the body step number 2 is to choose a reference system. Step number 3 is to determine the projection of the forces. Step number 4 is to project the equation sum of forces is equal to 0 into its different component. So we will admit the following steps in order to solve this vectorial equation, and they are very similar to the steps that we have followed in the barycentre formula. Okay, so let me start by exercise number 1. So let me repeat the steps. So the first step is to list the forces acting on the body. The second step is to choose a reference system. The third step is to determine the projection of the forces. And the step number 4 is to project the equation sum of forces is equal to 0 vector into its different components. So when we do apply sum of forces is equal to 0, or we use Newton's second law whenever we are interested in determining the magnitude of a force or something related to the force, whether an angle or a magnitude. Okay, so whenever we are interested in determining, say for example, the magnitude of a force or something related to the force which is given by an angle, then we need to apply Newton's second law. Now let's take exercise number 1. They are telling me the adjacent figure shows lion of mass 15 kg on a swing at equilibrium. So this gives us a hint that we must use the condition of equilibrium. Then number 1, they are telling me determine the magnitude of the tension T. So this can be determined by applying Newton's second law. So here, for example, we can say apply Newton's second law. So before doing so, let me write here on the scratch the different steps that we usually follow in order to determine or to solve the equation. So step number 1 is to list the forces. Step number 2 is to choose a reference system. Step number 3 is to do the projection. And step number 4, project sum of forces is equal to MA, whether A is equal to 0 or no. Then now let me redraw the figure. Okay, so let me redraw the figure here. So already the forces are being listed on the figure, so we are done with step number 1. So let me redraw the figure here and represent the reference system. So suppose that this is the x-axis like this, and this is the y-axis like this. So this is x, and this is y. So this is the unit vector I, and this is the unit vector j. Okay, here we have a dotted line like this, and this is the tension T vector along the rope on which lion is swinging. So this is the T vector tension. This is the angle theta. This is the vector having magnitude 180 newtons, and this is the weight given by W. Okay, and here we have that the mass is equal to 15 kilograms. Okay, so we are done with step number 2. Now let's project the forces, and let's suppose that the name of this force is given by F. So this is F is equal to 180 newtons. So let's determine the projection of the different forces. So we have the force W. So notice that W is lying completely on the y-axis, so Wx is equal to 0, and Wy simply is equal to minus W because it's pointing in the negative direction of the y-axis. So notice that if this is the angle theta, so this angle will be theta because this line is parallel to this line, and this is simply pi by 2 minus theta. So in this case, Tx, so the force T. Now Tx, notice that Tx is pointing in the same direction of the x-axis T, so it's plus T times the cosine of the angle between T and x, which is pi by 2 minus theta. So this is Tx is equal to T sine theta, and Ty, let me place these in the boxes in order to refer to them directly. Now T is pointing in the positive direction of the y-axis, so it's positive T cosine theta. As for the force F, so Fx, notice that F is completely lying on the x-axis in the negative direction, which is minus F. So these are the forces. We are done with step number 3. Now we need to refer to this equation, sum of forces is equal to ma. So let's say apply Newton's second law, which is given by sum of forces is equal to ma, but in this case the acceleration vector is 0 because it is at equilibrium. So whenever the object is at equilibrium, no need to mention Newton's second law. We can directly say, or at equilibrium we have that sum of forces is equal to 0 vector. So in the case of the condition of equilibrium, no need to mention Newton's second law, we can directly say at equilibrium. Okay, so no need to mention Newton's second law. So at equilibrium, so notice that this is a vector equation. Vectors must exist on the left and vectors must exist on the right. So sum of forces represent the different forces acting on ion, and this is given by weight W plus the tension T plus the force F. And on the right hand side of this equation, this is the 0 vector. So now we are in step number 4, and we want to project this equation. So let's do the projection on the x-axis. Now how do you project on the x-axis? Simply we drop down the vectors, and each vector quantity will carry the label x. So this is Wx plus Tx plus Fx is equal to 0. Now the value of Wx is 0. So notice that we are interested in determining the value of T, and T appears along the x-axis and the y-axis, so we need to project along the x and along the y. So plus T sine theta plus the value of Fx is given minus F is equal to 0. So this is simply T sine theta minus F is equal to 0. So this is the first equation. Now we need to project on the y-axis, so let's do the projection on the y-axis. So now the projection on the y-axis is given by that we drop down the vector quantities, and each vector quantity will carry the label y. So here we have wy plus ty plus fy is equal to 0. So the value of wy is given by minus w plus the value of ty is given by t cosine theta, and the value of fy is given by 0. Let me mention here that fy is equal to 0. So minus w plus t cosine theta is equal to 0. So this is equation number 2. Now we need to solve these two equations. That are given by equations 1 and 2. Notice that in number 1 they are telling me to determine the magnitude of the tension T. So this is for part 1. Now we need to refer to part 1. We need to refer to these two equations in order to solve T. Notice that here the mass of Lion is given by how much? 15 kilograms. And let me say that take G is equal to 10 newtons per kilogram. So if mass of Lion is equal to 15 kilograms, then the weight, which is equal to m multiplied by g, which is equal to 15 multiplied by 10, which is equal to 150 newtons, and the magnitude F, which is given by 180 newtons. So we know the value of W and we know the value of F, representing the magnitudes of the vectors W and F. So we know W and we know F. Here we have two unknowns. We have T as an unknown, and we have the angle theta as unknown. And this is important because notice that this vectorial equation leads into two unknowns, and they are given by leads into two equations. So the number of unknowns must be equal to the number of equations, and I will write this as a note. So now in part 1 we need to find the unknown first, which is T. So for this reason we need to get rid of sine and cosine, and this can be done by using sine square theta plus cosine square theta is equal to 1, as we have done for the trajectory. So in this case, if t sine theta minus f is equal to 0, so sine theta is simply given by f divided by t, and if minus w plus t cosine theta is equal to 0, so cosine theta is equal to t divided by w, so w divided by t. Now using the equation that, which is given by cosine square theta plus sine square theta is equal to 1, so here we have the w divided by t to the power 2 plus f divided by t to the power 2 is equal to 1. Now, which means that w square divided by t square plus f square divided by t square is equal to t square divided by t square. So simplifying out by t square, because 1 may be written as t square divided by t square. So we know the value of w and we know the value of f. Therefore t square is equal to 150 to the power 2 plus 180 to the power 2. Now plugging this on the calculator, so this is given by 54,900. So the value of t, which is the square root of this, Notice that here the square root gives us two solutions that are given by plus and minus, but we are always interested in the positive solution. So square root of this number is given by almost 234.31 newtons. So the value of T is given by 234.31 newtons. Okay, so this is the value of T. Now moreover, in part 2 they are telling me to determine the angle theta. So now we are in part 2. Now in order to determine the angle theta, we can either refer to the equation number 1 or equation number 2. Let's refer to equation number 1, which is given by T sine theta minus F is equal to 0. Now we know the value of T and we know the value of F, so we can determine the value of sine theta. Sine theta is equal to F divided by T. The value of F is given by 180, and the value of T is given by 234.31. So plugging this on the calculator, so sine theta is given by 0.77 almost. And recall that sine theta is a dimensionless quantity, simply here because we are dividing in Newton by Newton, so they cancel out. Always the unit of sine and cosine is 1, so sine theta is equal to 0.77, and using our calculators, then theta, which is equal to sine minus 1 of 0.77 in degrees, is given by almost 50 degrees. Okay, so the value of theta is given by 50 degrees. So this is it for exercise number 1. And now let me make the following note. Sum of forces is equal to MA, or even sum of forces is equal to 0 when projecting in 2 dimensions it yields to 2 equations, one equation along each dimension. So in this case we have one equation along the x-axis, one linear equation along the x-axis, one linear equation along the y-axis. In order to solve the problem completely, the number of equations must be equal to the number of unknowns then the problem must involve, okay, without this statement because later I will generalize. So the number of equations must be equal to the number of unknowns. Okay. Now let's move to exercise number 2. They are telling me, as shown in the adjacent diagram, Diana applies a constant force of magnitude 300 newtons. So what's the type of this force? This is a muscular force along the handle of a roller, which makes an angle 30 degrees with the horizontal. The roller of mass 40 kg moves with a constant speed on a rough ground. So M is equal to 40 kilograms. Okay, and they are telling me to take G is equal to 10 meter per second square. So this is exactly the same as 10 newtons per kilogram. Later we will see the relation between meter per second square and newton per kilogram. Now in number 1, they are telling me characterize the force exerted by the handle on the hand. So let me change this question and say that list the forces. Let me change this question. Let me change the question of part 1 and make it as the following. So list the forces acting on the roller. Okay, so now let's list the forces acting on the roller. So because the roller has a mass, then it will be submitted to the weight W, and because we have a support, it will be submitted to the reaction at the support, which is the normal N. It is submitted to the muscular force or here they didn't specify if this handle is a string or no. Okay, so let's suppose that this is simply 300 newtons is a muscular force, and in addition to that they are telling me rough ground, and by rough ground means that the surface of contact between the roller and the ground is rough, which means that the force of friction exists. So here we have an additional force which is given by the force of friction, or the friction force, denoted by small f. So these are all the forces acting on the roller. Now in number 2, we need to determine the magnitude of the force of friction assumed to be constant. So for sure this can be done by applying Newton's second law to the roller. Apply Newton's second law to the roller. And this is very important because I have specified the roller. Later in part 3 or 4 probably I will talk about it, because we can apply Newton's second law to several objects, and here we must follow several steps in order to determine the magnitude of the force. And so okay, why we thought about using Newton's second law? Because in number 1 they asked me about the forces acting on the roller. Moreover, because Newton's second law allows us to determine properties related to the force, and in this case we are interested in determining the force of friction. Okay, so step number 1 is to list the forces or represent them. Step number 2 is to choose a reference system. Let me see the order of the steps is correct. Yes. So step number 3 is to project the forces. And step number 4 is to use the equation sum of forces is equal to ma, and project along the x and the y. So project along the x and on the y. Now sum of forces is equal to MA, and in this case A is equal to 0, and the reason is given by constant velocity. So the reason behind that the acceleration is 0 is not because the roller is at equilibrium. The roller is moving, so it is not at equilibrium. But the correct reason is that the acceleration is 0 because simply they are telling me at a constant speed. So in this case, now we are done with the step number 1, which is listing the forces. Now we need to choose a reference system. So suppose that this is the x-axis. Let me draw it here. This is the x-axis, this is the y-axis. So here we have the muscular force F due to Diana. We have the weight, which is acting vertically downward like this. We have the normal and the point of application, which is the point of contact between the roller and the support. So this is R. Moreover, here at this point we have the friction force. The friction force may be like this or like this. So recall that, okay, the reaction of the support is perpendicular to the support. The force of friction is along the support. Now notice that the roller may move like this, so the force of friction will be directed and is in a direction such that it opposes the direction of motion. Now I will represent these forces on the following reference system. So this is X, this is Y. So the force of Diana is making an angle 30 degrees with the horizontal. This is capital F, 30 degrees. This is the origin O. This is the unit vector I. This is the unit vector J. So here we have the weight, which is acting vertically downward like this. And this is the force of friction, which is acting vertically, horizontally to the left. And we have the reaction at the support, which is acting vertically upward like this. Now notice that the point of application, so I have chosen this point to be the origin, which is O. Notice that R has a point of application, which is the point A, point of contact between the roller and the support, but the R vector can be moved upward. Similarly to the force of friction, the force of friction can be moved upward because it's parallel to the x-axis, okay? So now we are done with the step number 2, and we have listed the forces after we have chosen a reference system. Now step number 3, we need to project the forces. Let's project them. So we are still in number 2, in part 2. Now let's start by the force, capital force F, which is the force due to Diana. Now Fx, notice that x is pointing in the same direction of the x-axis, so it's plus F cosine 30. Now cosine 30 is given by radical 3 over 2, if I'm not wrong. Yes, so radical 3 over 2 multiplied by F. If this is 30, this is 60. So in this case, Fy is simply given by plus F sine 30, which is equal to half F. So Fx is equal to radical 3 over 2 capital F, and Fy is equal to half F. Now as for the reaction at the support, which is the force R, so it's completely parallel to the y-axis, so Rx is 0 and Ry is equal to plus R. Now the force W, so Wx is completely 0 because w is parallel to the y-axis, and wy is given by minus w because it's pointing in the negative direction of the y-axis. This is 0 here. And now as for the force of friction, so it's completely lying on the x-axis in the opposite direction, so it's minus f, and fy is simply 0. Okay. Now notice that if you consider both parts, part 2 and 3, they are telling me determine the magnitude of the force of friction. So this is the first unknown, which is F. Now the force of friction is given by a vector. When they are telling me the magnitude without the vector, this is the first unknown. The second unknown, they are telling me determine the magnitude of the normal reaction, or the reaction at the support R. So its magnitude is simply given by R. So how many unknowns do we have? We have F and R if you are considering parts 2 and 3 as the same part. And because we have two unknowns, we need two equations to solve this problem, and they are given by the projection along the x-axis and the projection along the y-axis. But if we now are solving part 2 alone, we are interested just in determining the force of friction. So the magnitude of the force of friction only appears in the x component and not in the y component. So let's project along the x-axis only. So here we have that the sum of forces is equal to 0. So sum of forces is equal to 0. Then let's do the projection along the x-axis. Now the sum of forces is equal to 0 vector. Let me write here that this is given by the weight plus the reaction at the support plus the muscular force plus the force of friction. Now how do you project along the x-axis? So we drop down the vectors, and each vector quantity will carry the label x. Now wx is given by 0, rx is given by 0, plus capital Fx, which is given by radical 3 over 2f, plus small fx, which corresponds to the magnitude of the force of friction. So in this case, root 3 over 2 capital F minus F is equal to 0. So this is the first equation. Now before we proceed to the projection along the y-axis, let's check if this is sufficient in order to determine the value of F. So notice that capital F is given by how much? 300 newtons. So recall that this is capital F, and the value of capital F in magnitude is given by 300 newtons. So capital F is given by 300 newtons. So in this case, no need to proceed to the projection along the y-axis because then we know the value of F. So as for small f is given by root 3 over 2 capital F, which is equal to root 3 over 2 times 300. So plugging this on the calculator, then this is given by 259.81 newtons. So F is given by 259.81 newtons. So this is it for part 1. Now in part 3 they are telling me determine the magnitude of the normal reaction. So a normal reaction, which is R, appears in the y component. Already we have made use of the x component, so it's reasonable to project along the y-axis in order to determine the value of Ry. Now let's do the projection along the y-axis. We are projecting the equation which is given by W plus R plus T, plus capital F plus small f, which is equal to 0 vector, because the roller is moving at a constant speed. Because we are projecting along the y-axis, so each we drop down all the vector quantities, and each vector quantity will carry the label y. So this is wy plus ry plus capital Fy plus a small fy is equal to 0. Notice that capital Wy is given by minus w if we refer to these components, and capital Ry is just r, plus capital Fy is 0. Capital Fy is given by half f plus Fy is 0 because the force of friction completely lies on the x-axis. Now in this case they are telling me to calculate the magnitude of the normal reaction, which is r, so we are interested in determining the value of r. Notice that the weight is equal to m multiplied by g. The value of the mass of the roller is given by 40, and the value of g is given by 10. So 40 multiplied by 10, this is equal to 400 newtons. So we know the value of W, we know the value of F, we know the value of F because it's given to be 300 newtons. So what's the type of this equation? This is a linear equation and one unknown. The unknown is capital R. Then R is equal to W minus half F. Now the value of W is given by 400 minus half multiplied by 300. So 400 minus 150, this is equal to 250 newtons. So the magnitude of the normal reaction is given by 250 newtons. So here notice that in order to determine the value of F, we use the first equation, and in order to determine the value of R, we use the second equation. So this is it for this exercise. But now if we refer back to the first exercise that we have solved, the unknowns were given to be T and theta, and the equations are given by 1 and 2. Now notice that because equation 1 because the unknowns are T and theta, both of them exist in the first equation and both of them exist in the second equation. In such type of equations, we need to solve simultaneously in equations 1 and 2, as if we are saying that x plus y is equal to 2 and x minus y is equal to 5 is equal to, say for example, 0. So in this case, both variables exist in the first equation and the second equation, so we need to solve simultaneously for the equations 1 and 2. So this was what happened in the first exercise. But in the second exercise, what have happened here is that the projection along the x-axis gave us an equation of the form of ax plus b is equal to 0, in which we have one unknown, which is x. Similarly for the second equation, which is given by also in the form of cx plus d is equal to 0, and the unknown is x, or say for example y. cy plus d is equal to 0. So here both equations are linear equations and one unknown, whereas these equations are linear equations and two unknowns. Okay, so usually linear equations and one unknown are solved by putting the variable on one side and all the other numbers on the other side, whereas linear equations and two unknowns we need to solve simultaneously. So this is it for me in this video, guys. In the next part 3, we'll complete solving exercises on this chapter.